Hello students. In this lecture we will be discussing about the various methods that we use in the analysis of a determinate structure. In the previous lectures we have discussed how to calculate indeterminacy, how to calculate static indeterminacy. Also we discussed how to calculate kinematic indeterminacy. Uh, Basically what is the need of calculating the both. Also in this lecture we will discuss what are various different methods for the analysis of a determinate structure, and we'll also try to understand the suitability of certain method for a problem. Also we'll discuss some of the problem examples using some of the methods of analysis in the structure. So let's begin. Myself Shubhranshu Jaiswal, assistant professor, BCE University, Lucknow. So Uh, we'll start with the various types of indeterminate structure. Uh, for example, this is a case of prop cantilever beam. This is a kind of indeterminate structure. The structure is having one fixed support and the other is roller support. Uh, in this case, there are total three internal reactions because this is a fixed end. One, two, three. This at the roller end, we already know the total number of internal reaction is 1. The total number of internal reactions in this beam will be 4, and the 4 minus 3 is equals to 1. So this is an indeterminate structure. This is a case of a prop cantilever beam, and it is an indeterminate structure to a degree of 1. Now, see, we can simply see how we can make this structure as a determinate. We can simply remove this end to make it as a determinate structure. This will, if we remove this roller end, then what will happen? This we can simply here we will try to understand how to convert this indeterminate structure to a determinate structure. Simply, either we can do one thing, we can remove this support and the structure will become like this. As we can see in the part B, it will have only fixed end, and this is a case of a fixed beam. So here we have eliminated this support condition and we have converted this structure to a determinate structure. Now similarly, the other thing which we can do in this case is we can remove this fixed end and we can convert it to a hinge support. So in this way, if we substitute this fixed end with a hinge support, then this will become a simply supported beam, and we can know that we can clearly see that the number of reaction at this end will be 1, and here it will be 2. Total will be 3. 3 minus 3 will be 0. So this in two ways we can convert this structure into a determinate structure. Now, similarly, see this is the cases. We know the forces for this structure. Now, similarly, this is a fixed beam. We know this fixed beam is also a indeterminate structure. And for this indeterminate structure, for this fixed beam, the both ends are fixed. At each fixed end, there will be number of three number of internal reaction. Total number of internal reactions will be 6, and 6 minus 3 will be 3. So we can simply say that a fixed beam is a case of an indeterminate structure. Similarly, here also we can convert this structure to a determinate structure either by eliminating this end. So this will become a cantilever beam. This will become a cantilever beam, and similarly, in this case also we have already seen that by eliminating this support, this has become a cantilever beam. Similarly, here also, if we eliminate this support at point B, this will become a cantilever beam. Or we can substitute this support A with this hinge support, and the structure will become a simply supported beam. So, we have simply seen the ways we can convert a determinate structure to indeterminate structure to a determinate structure, and this approach will be used in the various methods for the analysis. Because first the approach will be, we will first convert indeterminate structure to a determinate structure, and then we will be analyzing the same. Now, what are basic commonly used methods for the analysis? Basically, we can see that there are two general methods of analysis. First is a force method, and the second is a displacement method. Now, what is a force method and what is a displacement method? We will study this in the upcoming lectures, and the whole chapter would be based on these methods. But here we need to understand the basic understanding we will develop here about the importance of the two of the methods. Force method is also known as a compatibility method, and displacement method is also known as a equilibrium method, and we can also call force method as a flexibility coefficient method. Similarly, we can also term this displacement method as a stiffness coefficient method. Basically, there are two basic methods of force structural analysis of indeterminate structure. One is force, other is displacement. Again, we can say force method, we can say it as a compatibility method, and we can say it as a flexibility coefficient method. Similarly, the displacement methods can be termed as a equilibrium method or a stiffness coefficient method. There are various different types of methods that comes in the category of force method and this displacement method. Now, other is now displacement methods. These are some of the example of displacement methods. Uh, we can see clearly here. Now, these are some of the methods of displacement method. First is slope deflection method. The other is moment distribution method. Next is Carney's method. This is also known as rotation distribution method. And the last one is stiffness matrix method. Basically, these are the methods, and we will study slope deflection method in the upcoming modules. Moment distribution method we'll also discuss in upcoming modules. Uh, this is stiffness matrix methods. We'll also discuss in upcoming modules. So now we come to force methods. What are basic force methods? Three moment theorem of three moment or moment area theorem. This we have already studied in the structure analysis one. Method of consistent deformation. This method we will discuss in the upcoming modules. Elastic center method. This is also a method that is used to calculate the force method. That comes under, basically it comes under the force method for the analysis of indeterminate structures. The strain energy method is also comes under the force method, and this we have already studied in the structural analysis one. Now the other is flexibility matrix method, and this will be also discussed by this. I'll discuss this in the upcoming module. So many of the methods we have already studied, and many we'll discuss in the upcoming modules. Now there are some other methods of analysis of indeterminate structure, that is moment area method again, and conjugate beam method. Both we have discussed both the methods in a very descriptive manner in the structural analysis one. Moment area method, also the conjugate beam method, and these are the methods which becomes a base for the analysis of indeterminate structure. So both of them are very important, especially the conjugate beam method, because it is a base for the flexibility analysis of structure, flexibility as well as flexibility method for the analysis of structure, and slope deflection method is a base for stiffness matrix method for analysis of indeterminate structure. So we some of the methods that are we have already discussed in the past will play a crucial role in the analysis of upcoming methods for the indeterminate structure. Now, what is the suitability? I would like you all to understand this thing very in a very good manner. At what is the suitability of a method for selecting a appropriate method for any cases? So simply we'll see we have already in a condition where we can easily calculate the kinematic as well as static indeterminacy of any of the structure. So if the degree of kinematic indeterminacy is less than degree of static indeterminacy, again I will repeat this. If degree of kinematic indeterminacy is less than the degree of static indeterminacy, in such case we will be preferring the displacement method for the analysis. And if the condition reverses, like the degree of static indeterminacy becomes less than the degree of kinematic indeterminacy, then we use the force method. So first of all, what we'll do, we'll calculate the degree of static as well as kinematic indeterminacy, and then we can decide which of the methods to choose from displacement or the force method. Now, this is example. Here we can see basically in this case, this is a hinge support, this is a roller support, this is also a roller support. The degree of static indeterminacy in this case is 3 minus 2. 3 because um this is 2, this is this. Yes, we can see over here. In this case, total number of static indeterminacy will be the DS. Let's do not consider this thing; it will make confusion. But the answer will be same. I'll show you how. This is a hinge support. Here, the number of internal reactions will be 2. Here 1. Here 1. It is 5. Total is 5 minus 3. That is 2. Number of this is case where the static determinacy have become is equals to 2. Now if we calculate the kinematic indeterminacy in this case, then the kinematic indeterminacy will be the degree of freedom for this. And the degree of freedom, if we see for this case, this will be is equals to 1 here, 2 here, and 2 here. So total degree of freedom is 5. So in this case, we have seen that degree of static indeterminacy is lesser than the degree of kinematic indeterminacy. So in this case, we will be preferring force method to analyze this structure. Similarly, in this case, this is a fixed beam. Both ends are fixed. The degree of static indeterminacy will become is equals to that is 3 here, and 3 will be here. So it is 6 minus 3, that is equals to 3. In this case, the degree of kinematic indeterminacy is 0. We will not consider these cases. We'll only consider this as a fixed beam. So in that case, the degree of freedom of this support is 0. This support is also 0. The total degree of kinematic indeterminacy will be 0. Where here we are only seeing the degree of freedom. So in this case also, the degree of static indeterminacy we have seen, it is greater than degree of kinematic indeterminacy. Hence, we will prefer displacement method for the analysis. So this is how we will be choosing appropriate method for the analysis of different indeterminate beams. Now Now, we'll quickly review some of the upcoming methods that we'll study in the upcoming modules. Flexibility of force or consistent deformation method. Force method of analysis, also known as the method of consistent deformation, uses equilibrium equations and compatibility conditions to determine the unknowns in a statically indeterminate beam. We know already in terms of analyzing a structure, we are concerned with equilibrium conditions, and the number of compatibility equations exceeding the equilibrium condition is the number of degree by which the structure is indeterminate. So we'll be doing that in the force method of analysis. In this method, the unknowns are redundant forces. Obviously, redundant forces are the unknown forces. Basically, the forces are in this method. The unknowns are the redundant forces. A redundant force can be an external support, reaction, or internal member, which if we remove, the structure will cause any instability, will not cause any instability. So this is a basically approach of analyzing this structure using flexibility matrix method, or a consistent deformation method. What we do, will simply remove any of the support condition or modify it in order to convert it into a determinate structure. Then we'll simply analyze the structure using the conditions available. Now, again, for the same flexibility method, This method entails formulating a set of compatibility equation depending upon the number of redundant forces. Okay. Now the redundant forces are known. The structure become determinate. That is what I told you, and then can be analyzed completely using the conditions of equilibrium. The basic approach in this method will be, first of all, we'll modify the support conditions, and we'll try to convert an indeterminate structure to a determinate structure, and then we will be analyzing this transformed determinate structure by using the equilibrium conditions. Now, the other one is direct stiffness method. What is direct stiffness method? Direct stiffness method is also known as a matrix stiffness method. This method we will discuss in the I think well, in the upcoming modules. We'll discuss this method in a very descriptive manner. This is particularly suited for computer automated analysis of complex structure, including the statically indeterminate type. Okay, so basically, in this method, this is very common method used nowadays. It's totally based for computer programming, like very the uh, finite element analysis. The basis is the stiffness matrix method, where we develop the displacements coordinate for different cases, and we form a matrix for it, and the same can be analyzed using the computer programming such as stat and etc. Now this is also this makes a member stiffness relationship for computing member forces displacement. We calculate different displacement coordinates for different member of a structure, and then we assign a matrix, we do the analysis for the same matrix for under this method. We'll come to it when we'll study this method. We'll be uh, having a much broader view for the same method. This is what I told you. We use it is a basic of finite element method such as stat pro and etc. Okay. Now, very important method. This is, we have already discussed in structure analysis one. Here again, we'll see the application of it. Conjugate beam methods. Now, basically, there are certain conjugate beam theorem says something, and according to the conjugate beam theorem, there are certain rules which we uses in while the analysis of a structure using conjugate beam method. First one is if in a real beam. Now see if a real beam is like this end is hinged, this is an internal hinge, and this is a intermediate support. So what happens in a conjugate beam, the real beam for a conjugate beam, if the support is fixed in the real beam, then it converts to a free end in case of a conjugate beam. So this is a beam consists of one fixed end, one internal hinge, and one intermediate support. If we will draw a conjugate beam for this beam, then it will be like this. Here the fixed end has turned to a free end, the internal hinge turns to a intermediate support, and the intermediate support is turns to is converted into a internal hinge. Here it is converted into an internal hinge, and the free end becomes a fixed end. The rules are simple. Free end become fixed end, fixed end become free end, internal hinge become intermediate support, and intermediate support become internal hinge. Other case, if the real beam is like this, then the free end have become fixed end, intermediate support has converted to internal hinge. Again, the roller support, if there is a roller support will be as it is in the case of conjugate beam. So if there is a roller support, it will be same as roller support in case of a conjugate beam. Now this is another case. Here if hinge is there, this is a hinge support, and this is the intermediate support. Remember, this is corner support, this is a hinge support, and this is the intermediate support. Intermediate support always lies between the beam. This is at the end. So if there is a hinge support, it will be remain as hinge support. Roller, we know, it will become roller as well, will be same as roller as well. Another case, here this is a hinge support, will remain hinge. This is a intermediate support, will convert into a internal hinge. Again, this is the intermediate support, this will be converted to internal hinge. This is again a roller support, this will be same as roller support. In this case, This end is fixed. This is a hinge. This is again hinge, and this is all. This is a roller support. So in this case, the fixed end will become free. The internal hinge will become intermediate support. Same here, and same in this case. The roller support has remained the roller support in the case of conjugate beam. Now we'll discuss one example in here in which we'll see how we have analyzed this beam using the uh, conjugate beam method. Here, the question is determine the support reaction of a propped cantilever beam. Uh, Here we are concerned with calculating the support reaction. This is also a part of analysis. This is a cantilever, a propped cantilever beam. This is the case of an indeterminate structure because here the total number of reactions are 4. Equilibrium condition is 3. 4 minus 3, that is 1. So it is an indeterminate to degree of 1. So what we in this case the length is L, and the point load of P is acting in the middle of this span L. So distance from A to this point load will be L by 2, and from point B to this point load will be L by 2 as well. So now in this case the static indeterminacy of the beam uh, is 1. That is 4 minus 3 is equals to 1. Now the corresponding conjugate beam of the propped cantilever will be shown in the next figure. I'll make. Now the reaction R is the reaction that is developed at the prop support. In the prop support here, the reaction upward reaction of R will be developed due to the support condition. Now we can easily see this is a beam and this is a conjugate beam for this. Now we need to understand this in a very concentrated way because and we have already discussed this in this method in the structure analysis one. So here we'll quickly see about it. Here, due to we need to understand this is a basically loading diagram, and this loading diagram becomes the basically the M upon EI diagram. According to conjugate beam theorem, the M upon EI diagram for the real beam becomes the loading diagram for the conjugate beam. So here for this beam, if we first see and make M upon EI diagram, it will be like this, and this M upon EI diagram has turned to a loading diagram for the conjugate beam. So here we have seen the free, this end was fixed, so it has become free according to conjugate beam theorem, and this was roller. It has remained to be a roller support. Now for if we see for solely if we see for this part, this if we neglect this load P for cantilever beam, this will be the whole bending moment, and uh, for if we consider this load, then this will be the M upon EI diagram. It will act downward. So R upon L EI, this will be the height of this part, and PL upon 2 EI will be height of this part. The center of the center of this loading diagram, this is a triangular loading, will be this, and this will be 2L by 3 from this end, and L by 3 from this end. And the L will be the span, the whole span. Similarly, in this case, this is the CG of this loading diagram, and it will act upward. This one will act downward. Now, for this, the length is L by 2. So this will become L by 2 divided by 3, because the CG will be L by 3, and the length over here is not L. It is L by 2. So it will be L upon 2 divided by 3. That is L by 6. So here we can see the calculation how we have got this thing. The unknown is obtained. So in this case, if we calculate the total loading, what we'll do, we'll simply take a moment over here. We have taken a moment to end B. uh, what will be the moment? That this load value is PL by 2 EI. This is the height. The total load of this figure will be half into base into height. The base is L by 2. The height is PL by 2 EI. So this is 1 by 2 multiplied by base is L by 2. This is L by 2. and the height here is PL by 2EI. PL upon 2EI is the height. So this is creating a hogging in this in this case. Sorry, this is creating a sagging in this case. So it will be minus, and then this loading is half into base into height. The height again here is RL by EI, and the base will be total L. Okay, before this we will understand this term first. Now for this one, for this part, half multiplied by basis this one, multiplied by height is this one. This is the load, total load, and what will be the moment at point B due to this load? This will be total load multiplied by this distance, and this distance will be what? This will be L by 2 plus L by 3. L by 3 is this distance and L by 2 is this distance. So L upon 2 plus L by 3. Now this will be, uh, for this one, the loading will be half into base, that is L, into height, that is RL by EI. Now what is the distance it from the CG? This is 12 upon 3. So this is the equation for this loading. From here we can easily calculate R, that is 5p upon 16. So this is what we were concerned with in this question. And this question we need to calculate the reaction, support reaction R at the end B using the conjugate beam theorem, and we have calculated R to be 5p upon 16. So another thing we'll discuss shear moment and load rotation. Basically, we will be in the next class we will be discussing about different method for the same beam, different method for analysis, that is integration method, uh, and we'll discuss uh, uh, the same method, that is integration method for the calculation of various things for the case of a prop cantilever beam. So, okay, I think class students, you would have understand this concept of analyzing a determinate structure or using conjugate beam theorem. Um, in the upcoming video, we will discuss the method of integration for the the analysis of prop cantilever beam. Thank you, class.